Now let us see this problem. An ebonite ball of radius 50 millimeter is charged electrically by friction with a uniformly distributed surface charge of density sigma is equal to 10 microcoulomb by meter square. The ball is rotated about its axis at 600 rotations per minute. Find the magnetic induction generated at the center of the ball. So you have an ebonite ball which is having a radius of 50 millimeter and it is charged by friction. Okay, and it has a surface charge density of 10 microcoulomb by meter square per meter square. The ball is now rotated. This ball is rotated about its axis at 600 rotations per minute. Okay, so find the magnetic induction generated at the center of the ball. So you are asked to find what is the magnetic field intensity at the center of the ball. Okay, so now let us consider a sphere. So I'm going to take a sphere. Okay, so let this be a sphere and let this be the center of the sphere. Okay, let me call it as O. Okay, and the sphere, now you can consider the sphere as made up of so many rings. Okay, so let me take one ring like this. So it is made up of so many rings like this. Okay, so this ring, if you see this ring, okay, this ring has a center somewhere here. So if you take this as this is the axis. Okay, so this is the axis and this is the radius. Which one? This is the radius. Okay, and this is the axis. So let me call that this point. Okay, somewhere at this point. So this is the center of this ring, O dash. Let me call O dash. Okay, so now this ring, our sphere is now rotating. Okay, sphere is now rotating about this axis at with certain angular velocity, right? With certain angular velocity, omega. Let me call it as omega. So the angular velocity omega, it is rotating and it is given as 600 rotations per minute. Now you can see that this ring is made up of so many, the sphere is made up of charge, so obviously this ring also has got certain charge on it. Now this ring, it rotates. I mean the sphere is rotating, so the charge in this ring is also rotating. So this charge, when it rotates, it produces a current. So it behaves as a current carrying coil, okay, or a ring, the current carrying loop. And this current carrying loop has a magnetic field on its axis. So every such loop, you can divide the sphere into so many such current carrying loops, and you can find what is the magnetic field at the center due to all these loops. Okay, that's what we are going to do here. So what we will do here is we'll take a small element. Okay, I'm going to take a small element on this ring. I'm going to take a small element. Okay, and this element, if you see, this element is lying on the surface of the sphere. Okay, on the surface of the sphere. Surface of the sphere. So you can see here, this is lying on the surface of the sphere. Okay, yeah, so now this is lying on the surface of the sphere. Okay, so let this angle be phi. Okay, so the point from so this is a small element, and the element, it moves from this point, the initial point to the final point. Let us say it rotates by an angle d phi. So this angle I'm going to take as d phi. Okay, so this is d phi. Okay, now I'm going to join from the center of the sphere to this element. Okay, so from the center of the sphere to this element I'm going to join, and also I'm going to join from this point O dash, okay, which is the center of the ring. So from center of the ring also I'm going to join. Okay, so from center of the ring also I'm going to join here. So here, since this is d phi, this angle is also d phi. This is d phi, this is also d phi. D phi. Okay, this is d phi. And this angle I'm going to take as phi, theta. This angle I'm going to take as theta. Okay, so this angle I'm going to take as d theta. Small angle. The small angle I'm going to take as d theta. Okay, so now this is radius, this distance from the center of the ring to the center of the sphere. Okay, this distance I call it as small d. Let me call it as small d. Okay, and the radius of this ring I call it as small r. Okay, and the radius of the circle, the sphere, you know, it is capital R. Okay, capital R. Now this angle is 90 degree. This is right angle, 90 degree, isn't it? This is 90 degree. So you can see here that certain trigonometric relations you can see here. That is, what is it? Small r is equal to r sine theta. Small r is equal to r sine theta. And small d is equal to r cos theta. Small d is equal to r cos theta, isn't it? So small d is equal to r cos theta and small r is equal to r sine theta. So there's certain relations you have, and now also small r is equal to d tan theta. Small r is equal to d tan theta. So these three relations you have, right? Small r is equal to d tan theta. Now here, for the first thing we have to find out is what is the area of this ring. Okay, so area. So will you find area? Area is equal to dA is equal to dl, length, into breadth. dl into dB, length into breadth. Okay, or simply you can write it as length into breadth. Okay, so this is length into breadth. Okay, so what is length? Length, if you consider this as the length, if you consider this, that is equal to r into d theta. Okay, and what is breadth? Breadth is equal to small r into d phi. Okay, and what is small r? Small r is r sine theta. So breadth is equal to r sine theta into d r sine theta into d phi. Okay, so this is your breadth. So what is your area finally? So the area comes out to be, you can see here, length into breadth. So r square, okay, sine theta, okay, d theta into d phi. So this is your area. See here, this is the area. Okay. This is the area. Area comes out to be r square sine theta d theta into d phi. This is the area. Okay, area of the small element. Okay, on this ring. This area is r square sine theta d theta into d phi. Okay, so now I'm going to find what is a current. Okay, for that you need to find what is charge. So you know that surface charge density sigma is given by dq by dA, right? So what is sigma, or what is dq? Okay, dq is equal to sigma into dA, right? So dq is equal to sigma into dA. What is dA? dA, you know, r square sine theta d theta d phi. Okay, so that means sigma into r square into sine theta into d theta into d phi. This is your dq. So current will, as you know, is given by dq by dt, dq by dt. Okay, and you can, you know that d phi by dt. Okay, d phi by dt is omega. You can see from this diagram, d phi by dt is omega, isn't it? D phi by dt. See this d phi is the angle at which it is angular displacement, rate of change of angular displacement. That is, d phi by dt is the rate of change of angular displacement. So it is omega. So the current I, which is dq by dt, if you see, it will come out to be sigma omega r square into sine theta d theta. So this is the current value of the current which you are getting. Okay, so current is sigma omega r square sine theta into d theta. This is the current. Okay, so you can see here that there's a current which is flowing in this ring. Okay, so this ring behaves as a circular current loop, and it has a magnetic field at this center. Okay, so what is the small magnetic field that is produced due to this small ring? The magnetic field produced at the center is how much? Mu naught I is the current. Okay, radius of the ring is r square by 2 into, you can see here that the distance from the center of the ring to the center of the sphere is, we are going to find the magnetic field at the center of the sphere. So the distance between the center of the ring and the center of the sphere is small d. Okay, so you can calculate here by 2 into r square plus d square into whole to the power 3 by 2. This is the magnetic field which is produced due to small ring. Okay, small ring which is having a radius of small r. Okay, and here we can use certain relations, certain relations which we already got here. That is, I is equal to sigma omega r square sine theta d theta. So I is given by sigma omega r square sine theta into d theta. Okay, and then you can use the formula r by d. R is equal to d tan theta. Okay, then you can use the relation d is equal to r cos theta, and also small r is equal to r sine theta. Okay, so small r is equal to r sine theta. So these are the relations which we use here, and when you substitute, you will get the magnetic field. Finally, the magnetic field comes out to be how much? The magnetic field comes out to be mu naught, okay, sigma r divided by 2 into sine cube theta into d theta. This is what you will get when you substitute all these values here, and when you solve it, you will get the magnetic field due to the small ring, okay, at the center of the sphere as mu naught sigma r by 2 into sine cube theta d theta. So in order to find the total magnetic field, it is you just have to integrate the magnetic field to the small element from 0 to pi. Okay, so you can see here that such rings are there right from the top to the bottom. Okay, at the top the angle is theta is 0. Okay, and at the bottom it is pi. So from 0 to pi you have to integrate. So you are integrating from 0 to pi. So when you integrate it, so the total magnetic field is, you can see here that this mu naught sigma r by 2 is constant. So mu naught sigma, and also one omega is there. So here one omega is there, right? Sigma r omega, mu naught sigma r omega by 2, right? So mu naught sigma r omega by 2 integral sine cube theta d theta. So from 0 to pi. Okay, and what is integral sine cube theta d theta? From 0 to pi, if you solve it, it comes out to be 4 by 3. Okay, So it is 4 by 3. So which means your magnetic field at the center will be equal to mu naught sigma r omega into, here 1 by 2 is there and 4 by 3. So when you solve it, finally you will get 2 by 3 mu naught sigma. Where what is the value of mu naught? You know, it is 4 pi into 10 to the power minus 7 Tesla meter per ampere. What is the radius? Radius is given as 50 millimeters. So 50 into 10 power minus 3 meter. And what is omega? Omega is 600 rotations per minute. So 600 into 2 pi by 60. That much radians per second. Okay. And then so sigma, and the surface charge density sigma. What is sigma value given? Is 10 microcoulomb. So that is 10 into 10 minus 6 coulomb per meter. So you know sigma, you know r, mu naught r and omega. So when you substitute, the magnetic field at the center comes out to be 2.6 into 10 to the power minus 11 Tesla. So this is the magnetic field which you get at the center of this sphere. Okay, so the sphere, you can consider the sphere as made up of so many thin circular current carrying ring or coil, and when you integrate it from top to bottom, you will get the total magnetic field at the center of this sphere. Okay, and the magnetic field comes out to be how much? 2.6 into 10 to the power minus 11 Tesla. This is the magnetic field. In this case, magnetic field produced at the center of the ball, the ebonite ball, is 2.6 into 10 to the power minus 11 Tesla. Okay, thank you.